Hi dear students, this is Sonon, Assistant Professor, Department of Chemistry, Local Education Society's Arts, Commerce and Science College, Jawar, District Palghar. Dear friends, in the previous part, we have completed the topic entitled as liquid state. In the study of liquid state, we have discussed about various physical properties of liquid state, and we also tried to discuss about the measurement of these properties with the help of different techniques. After the completion of chemical kinetics and the liquid state, now friends, we are going to start the new topic from the organic chemistry called as stereochemistry. Here, initially, we should know why there is a need to study the stereochemistry. Actually, normally, whenever we are representing the molecule or the structure of the molecule, generally we are using the 2D representation, two-dimensional representation. But actually, any molecule has three-dimensional structure. So to understand their properties, we must be able to visualize the structure of molecule in three dimensions. And in order to visualize the structure of three dimension with the help of 2D representation, the new branch is used, and that branch is called as stereochemistry. So here, dear friends, in order to know the three-dimensional structure of the molecule with the help of 2D representation, we are going to use a branch of the chemistry, and that branch is called as stereochemistry. Here stereos means that is regarding with the space, and therefore this stereochemistry is defined as the branch of chemistry which deals with the description of the spatial arrangement of atoms in the molecule in three dimension. That is simply called as the three-dimensional structure of the molecule. It means that the branch of chemistry which deals with the three-dimensional structure of the molecule is called as stereochemistry. So dear friends, in the study of stereochemistry, there are different ways to represent the molecule. By this representation, definitely we will get the information about the three-dimensional structure of the molecule. And the first method is called the flying wedge formula, which is also called as a wedge dot formula. And this is the most common method generally used for the representing the three-dimensional structure of the molecule. So according to this representation, what we have to do? As we are going to talk about the three-dimensional structure of the molecule, it means we are going to talk about the 3D structure. It means some part of the molecule will be present above the plane or towards the observer, and the second another that is again other part will be present below the plane or away from the observer, and the remaining part will be present in the plane. That is simply a way to understand with the help of the stereochemistry. So the molecule in this method, in this wedge dot structure or the wedge flying wedge formula method, the molecule is simply oriented in such way that the most oxidizable group in the molecule should be present at the top, and the groups which are present above the plane or towards the observer are always shown by means of a such type of the solid wedge or the heavy lines. This is important as per or according to this method, and the groups which are present below the plane or away from the observer, these are always shown by means of such type of the dotted or dashed lines, while the groups which are present in the plane of the paper, these are always shown by means of such type of the continuous line. Dear friends, definitely these are the rules. No one is going to ask you the rule, but you should know what is the representation according to this method, and definitely for that purpose we will use the structure. In this case, definitely here this is the solid wedge or the wedge line that indicates the group is above the plane, and this is the line that indicates the dashed line or the dotted line. It indicates the group is present below the plane, while these two remaining groups A and B, these are indicated by continuous line. So definitely it indicates these are groups are present in the plane of the molecule or in the plane of the paper. Here one of the example of this with the by this representation is indicated, and that is the simply lactic acid. So definitely this COH and CS3, these are present below the plane. Hydrogen and OH, these are present above the plane, and this carbon is present in the plane. Similarly, the same structure can be shown, or the same representation can be shown with the help of another example of glyceraldehyde. This is the simple way. Another projection formula to understand the chemistry structure of the molecule, and the first type of the projection formula is called as the Fischer Projection formula. This method is particularly useful for the compounds with two or more asymmetric stereogenic center or the asymmetric carbon, and in the Fischer projection is obtained by projecting the molecule so that the central carbon-carbon bond is parallel to the plane of the paper. So according to this projection, which projection? That is Fischer projection. According to the Fischer projection, the compound with two or more asymmetric carbon atoms are always represented in vertical position, having most oxidizable group present at the top, and all groups are eclipse. What is eclipse? What is the phi? That we will discuss later on. And the central carbon-carbon bond is always present in the plane, because this method is generally applicable for the compound which are containing more than one asymmetric carbon. That's why these two asymmetric carbon present in the plane of the paper, and then at this carbon-carbon bond, the vertical line indicates, or the vertical line on the n carbon atoms indicates these groups are present below the plane or away from the observer, while horizontal lines at the n carbon indicate these groups present above the plane or towards the observer, and the intersection of vertical and horizontal lines represent the carbon usually which is asymmetric carbon. If there is an intersection, definitely we will discuss all these rules with the help of this example. Particularly, suppose here in this case there is only one example, only one asymmetric carbon. That's why this is shown for the molecule containing one asymmetric carbon. Then this asymmetric carbon is in the plane. Vertical line indicates groups are present below the plane, and horizontal lines are indicating groups are present above the plane. So this is simple way. And definitely for the compound containing two asymmetric carbon, the same thing. Now this asymmetric carbon and this asymmetric carbon, which is the carbon-carbon single bond, and both are asymmetric carbons. These are present in the plane. This is the vertical. These are represented vertical. And at this n carbon as well as the n carbon, the whatever horizontal lines B and C and D and E, these are present above the plane, and vertical lines A and F, these are present below the plane. Here this is, I hope you can understood this. So these horizontal lines OH and H, these are present above the plane, and vertical lines COOH and CS3, these are present below the plane. So this is the Fischer projection representation. So this is the Fischer projection representation, and also we talked about the flying wedge formula. In the flying wedge, groups present above the plane indicated by solid wedge, and below the plane indicated by dotted line. And according to Fischer projection, the horizontal line indicates above the plane, vertical line indicates below the plane. That's why this is the conversion of Fischer projection into flying wedge. So here you can observe here as COH group and CS2, these are present on the vertical line. So these groups are present below the plane. Hydrogen and OH, these are present on that is horizontal line. It indicates these are present above the plane. Similarly, we can talk about the other example like this and this. Definitely you can go through the number of examples, but in this example, if we talk about the compound containing the two asymmetric carbon atom, then these two asymmetric carbon atom present vertically in the plane. So these are shown by continuous line, and COH and COH, these are on the vertical line, so these are present below the plane. That's why here these are indicated by dotted line or dashed line, and HOH, OH, these are present on the horizontal line. It indicates these are present above the plane, so these are shown by means of this solid wedge or the thick lines. Here again a number of examples are there, but in the Fischer projection there are some rules. The molecule should not be lifted out of the plane. We can rotate the molecule in the plane but not out of the plane. Again, it can be rotated either by 180 degree or the 360 degree in the plane of the paper, as vertical and horizontal substance remains unchanged. So here rotation of 180 degree and the 360 degree in the plane of the paper is allowed, but the rotation of 90 degree is not allowed. However, the rotation of 90 degree and 270 degree is not allowed in the Fischer projection because it changes the orientation of the graphs. Also, the configuration remains unchanged. Here it is very important. If any two groups are interchanged twice, then the configuration remains unchanged, and any three groups are rotated at a time clockwise or in anti-clockwise direction by keeping the four group, then the configuration remains constant, unchanged. Fischer projection is restricted to only one form called as eclipse form. So here Fischer projection formula indicates the eclipse form. Here the relative angle between the two substituent on adjacent carbon atom is 0 degree. That's why it is called eclipse. What is eclipse and stagger, that we will discuss later on. Now dear friends, these are some examples. I hope we can try this examples for the representation in, that is simply what we can say, that is Fischer projection. So there are a number of examples. Now this is the interconversion of Fischer projection into flying wedge. Already we talked about this example, so we are going to skip this example, but you should be able to practice these examples. How can we convert this Neumann projection into flying wedge? Now second method for the representation of the molecule, or the projection formula for the representation of the molecule, is called as the Neumann projection formula. According to this method, what he has to do, actually in this method the carbon the molecule is observed in such way that one carbon is present behind the other carbon, and the central carbon bond is perpendicular to the plane of the paper. So here this is one carbon is front carbon and the another carbon is the back carbon, and in the presentation or during the representation according to this method, the front carbon is always indicated by the center of the circle from which the three bonds are originated. How it that I will show you later on. While the back carbon atom is indicated by the circle itself, and its bonds will be originated from the periphery of the circle. Suppose this is the example. This is the one example in which this molecule is having the two carbon 1 and carbon 2, and in this Neumann projection formula, this molecule is observed in such way that one carbon is present behind the other carbon, and definitely the front carbon, and the another one is the back carbon. So front carbon is indicated by the center of the circle, and its bonds will be originating from the center of the circle, and the back carbon is shown by means of simply circle itself, and its bonds will be originating from the periphery of the circle, and this is the representation. This representation is called as the Neumann projection formula. Here you can see the relative angle between the two substituent and adjacent carbon, this hydrogen and this hydrogen, because this hydrogen is present on the front carbon and this hydrogen is present on the back carbon, and the relative angle between these two substituent and these two hydrogen is 0 degree. That's why this form of the conformation is called like the eclipse conformation, where the relative angle is 0 degree. And if one of the carbon, either the back carbon or the front carbon, is rotated by the 60 degree, then we are getting this arrangement. Here the relative angle between the substituent on adjacent carbon, this hydrogen front carbon, this hydrogen on the back carbon, is 60 degree, and if the relative angle between the two substituent on adjacent carbon is 60 degree, then that form is called as the staggered form. And in the Fischer projection, the Fischer projection formula represents this form of the molecule, that is eclipse form, and if it is rotated by means of 60 degree, we are getting another form in which the relative angle is 60 degree, called as staggered conformation. This is again very important. In the eclipse conformation, the relative angle between the substituent is 0 degree, while in the staggered conformation, the relative angle between the substituent is 60 degree. So this is the Neumann projection formula. I hope you can draw the same structures for the other molecules. Here already I talked about the eclipse conformation. The relative angle between the substituent and adjacent carbon atom is 0 degree. Then the conformation is known as eclipse conformation, while in the staggered conformation it is 60 degree. Now in this way, next one is the Sahar projection formula. Actually in this representation, the molecule is projected by holding it at particular angle to the plane of the paper in slanting manner, and the carbon indicated by the stick line, and the two ends indicate the two carbon at which the different groups are attached. So this carbon bond is indicated by this type of the slanting manner, and this end carbon that indicated by the ends of the stick, and definitely at which the three bonds are attached or different bonds are present, and this representation is called as the Sahar's representation. This is just like the Sahar running horse, that's why it is called as Sahar's representation. Again here relative angle between these two, D and A, is 0. Again this D and A is 0, that's why these two are the eclipse conformation, and here this A and F, the relative angle between this A and F is 60 degree. That's why these conformations are called as the staggered conformation. So remember that we can represent the staggered and eclipse conformation in Neumann projection as well as Sahar's projection. So this is not the problem, but Fischer projection simply indicates the eclipse conformation. Now this is the tartaric acid, in which definitely two asymmetric carbons are attached to the OH, COH and the H, and this is the eclipse conformation. This is the eclipse conformation of tartaric acid, and if this carbon-carbon single bond is rotated by means of 60 degree, then we are getting this type of the, or 180 degree, then we are getting this conformation in which the relative angle between the substituent is 60 degrees. So this is the staggered conformation. So in this way we are able to convert one conformation into another conformation, one projection formula into another projection formula of the same molecule. And during this, definitely we have to keep some things in mind. So how the central carbon-carbon bond is oriented with respect to the plane of the paper, are the bonds are present above the plane or below the plane or in the plane of the paper. Because whenever we are representing the same molecule by means of a different method, then and then the orientation of bonds or the orientation of groups should not be changed. So this is the important thing that we should keep in mind during the interconversion of molecule from one projection formula to another projection formula. Again, the interconversion should not affect the stereochemistry of the different asymmetric carbon atoms or the stereogenic center. So first interconversion that we can talk about the Fischer projection into Sahar's projection. So here in the Fischer projection, horizontal line indicates above the plane and vertical line indicates groups are present below the plane. So in the Sahar's, the central carbon-carbon bond is written in the slanting manner, vertical bonds pointing vertically downward direction and horizontal bonds pointed upward direction. So this is the important thing. So this is the Fischer projection, and this is the this is the Fischer projection, and this is the flying wedge formula. Now this CS3 is present on the vertical line, so it is above below the plane. This CS3 is also below the plane. Hydrogen, chlorine, these are on the horizontal line, so these are present above the plane. So here again, so we have to represent this molecule according to Sahar's, in which CS3 and this CS3 should be below the plane, carbon-carbon bond should be in the plane, and these two hydrogen and the two chlorine should be present above the plane. And this is the way, this is slanting in the plane, CS3 below the plane, and these two hydrogens, this is the average plane, so definitely this hydrogen chlorine are above the plane. So this is the conversion of Fischer projection into Sahar's projection. And if we will rotate this carbon-carbon single bond by means of a 180 degree, either front carbon or the back carbon, then we are getting this conversion of this staggered eclipse conformation into staggered conformation. So this is the staggered conformation, because the relative angle between these two substituents, any two substituents on adjacent carbon is 60 degree. That's why this is the staggered conformation. Now these are some homeworks. So dear friends, I request you to go through this example for the conversion of Fischer projection into Sahar's projection. So these are the different examples. Again, these are the another example. Definitely number of examples are given. Next, conversion of Sahar's projection into Neumann projection. Because in the Sahar's, definitely these bonds are indicating groups are above the plane. This CS3 and this CS3 groups are indicating below the plane, and this is the front carbon and this is the back carbon in the slanting manner. While in the Neumann projection, the molecule is observed in such way that one carbon is present behind the other carbon. There will be one front carbon and another one will be the back carbon. So front carbon in the Neumann projection is always indicated by means of its center of the circle, and its bonds will be originating from the center of the circle, while the back carbon is indicated by this back carbon indicated by means of the circle itself, and its bonds will be originating from the periphery of the circle. And definitely with respect to this front carbon, CS3 pointing in the downward direction, chlorine and hydrogen is on the right hand side, this is on the left hand side. Similarly, we can apply the same thing. This CS3 is also pointing in the downward direction with respect to CS3. One group is here and another group is here. So this is the projection that we call it as the Neumann projection. And if one of the carbon, either front carbon or the back carbon, is rotated by means of a 180 degree, then we are getting the Neumann projection in staggered conformation. Here in the relative angle between the two substances is 0 degree. So this is the this is also the Neumann projection, but this is the Eclipse conformation. And this here the definitely here the front carbon is rotated and here the back carbon is rotated, but both are the same conformation, that is called as the staggered conformation. Similarly, another example here, this can be also converted into this Neumann projection, and on the rotation of the front as well as back carbon we are getting the staggered conformation. Next feature, now in this way we talk about how we can represent the molecule in that is Fischer projection formula, Neumann projection and the Sahar's projection. But whenever we will talk about this projection formula for the same molecule known as tartaric acid, so we are able to draw the same molecule in different projection formula. Now this is the tartaric acid in the Fischer projection. Now here, I don't think it is necessary to repeat again. Horizontal line indicates groups are present above the plane, vertical line indicates groups are present below the plane. So this is the flying wedge formula of the tartaric acid, and definitely now in this way, this is COOH and COH, these are pointing in the downward direction. These two groups and these two groups are above the plane and these are in the plane. So in the source, this molecule can be represented here. Again here the relative angle is 0 degree, that's why this is the Eclipse conformation, and if the either front carbon or the back carbon is rotated by means of a 180 degree, then we are getting the staggered conformation of the tartaric acid. And here this molecule can be represented in the Neumann, front carbon indicated by the center of the circle, while the back carbon indicated by means of a simply circle itself. Now these are the bonds of the front carbon. COH bonds pointing in the downward direction, this is pointing in the downward direction, and with respect to COH, hydrogen left hand side, OH right hand side similarly here, while same can be applicable for the back carbon. COH is pointing in the upward direction. Now here it is pointing in the upward direction. So this is this, and definitely this is the the Eclipse conformation, this is the staggered conformation. Now same thing can be applicable for the tartaric acid. Already we talked about this, how we can convert this Fischer projection into flying wedge formula, flying wedge into Sahar's and Sahar's into Neumann projection. So dear friends, in this way we have discussed about the representation of the molecule with the help of various projection formula, either a Neumann projection, Fischer projection or Sahar's projection, as well as flying wedge formula. But with this we are able to know which part of the molecule or which bonds are present above the plane, which bonds are present below the plane, and which bonds of the molecule are present in the plane. And definitely it is very important. Actually this is the 2D representation, but this, with the help of this 2D representation, we are getting the information about the three-dimensional structure of the molecule, and this is the actual stereochemistry, and this is actually the called as stereochemistry. So dear friends, in the next part of the video we will talk about the different types of the stereoisomers. We will talk about their different types with the help of different example. So dear friends, we will resume in the next part of the video to talk about the different types of the stereoisomers and the stereoisomerism. Thank you very much.